Hello everyone, my name is Alperen Onat. I'm a freshman student in Bilkent University Electrical and Electronical Engineering Department, and this is my Physics 102 project titled Experimental Study of Kirchhoff's Laws. In this experiment, I designed a two-loop circuit with using breadboard to 1.2 kilo ohm, to 1.5 kilo ohm, and 1.8 kilo ohm resistors, bunch of jumper wires, two power supplies, an ammeter, a voltmeter. The aim was to verify Kirchhoff's current law (KCL) and Kirchhoff's voltage law (KVL) by comparing the experimental current and voltage values to the theoretical predictions. I first set both power supplies to 15 volts and then gradually decreased one of them to 0 volts in steps of 3 volts, while keeping the other power supply constant at 15 volts. For each setting, I carefully measured the current and voltage across all 5 resistors. The results showed a strong agreement between experimental and theoretical values. The total percentage error across all resistors was about 0.7%, which indicates that the experiment was performed with high precision. However, it's important to note that resistor R2 showed a significant deviation with an error of about 22%. This large error is likely due to the multiple factors. Small currents across R2 could have made the measurements more sensitive to small disturbances. Contact resistance at the breadboard connections might have altered the effective resistance, and slight inaccuracies in ammeter or voltmeter readings could have also contributed. These factors highlight that even small experimental imperfections can have a major effect, especially on low magnitude measurements. Interpreting the data, I observed that Kirchhoff's current law was satisfied. The total current entering any node was nearly equal to the current leaving it, confirming the conservation of electrical charge in system. Similarly, Kirchhoff's voltage law was verified. The algebraic sum of voltage drops and rises around each loop was very close to zero, demonstrating the conservation of energy within electrical circuits. Moreover, I plotted voltage versus current graphs for each resistors. The slope of these graphs provided the experimental resistance values through Ohm's law, where resistance equals voltage divided by current. Most of the experimental resistance values matched closely with the expected theoretical values, further supporting the accuracy of the circuit design and validity of Ohm's law. From a broader physics perspective, this experiment reinforced two fundamental ideas. First, that charge cannot accumulate at a node, supporting Kirchhoff's current law (KCL), and second, that energy cannot be created or destroyed in a closed electrical loop, which underpins Kirchhoff's voltage law (KVL). It also showed practically how voltage, current, and resistance are related proportionally according to Ohm's law, and how these simple relationships form the backbone of circuit analysis. In conclusion, this experiment not only validated important theoretical principles but also emphasized the crucial role of precision, good connection quality, and careful measurement techniques in experimental physics. Overall, it provided a very clear and practical understanding of fundamental laws that govern electrical circuits. Thank you for listening.